In this video, we're going to go over solving trig equations, and there's going to be a lot of examples, so it might get to be a bit of a long video. It's really like 2 days worth of lesson material, so I'd encourage you to split it up and just watch part of it now and part of it another time. But we're going to start with solving just some basic algebraic equations, and you can totally do these on your own. Pause the video, try these on your own, and then you can check your work against mine. I'll just do them really quick for you. And then after, we'll talk about the specific technique that each one of these equations shows. So in a few of these, we had to combine like terms. That's what letter A says here. Like here we had to add 1 to both sides so that we could get both of the constants on the same side. Here we had to add x to both sides so that we could combine those like terms. So of course that's a really common technique, is combining like terms when you're solving. Another one, it says use extracting square roots or factoring if necessary. And so we did that. We had to take the square root in this problem. And what's important to remember is every time you take the square root, it does make a plus or minus show up. And in number 4, we had to factor it. Here we had just the greatest common factor of x, and then we used the zero product property, if you remember that from algebra, just to split up this equation and solve both of its factors separate. So of course the general goal for solving an equation is to isolate the variable. And then here where it says solve for x within the domain, we didn't see that show up in any of these examples, but a lot of these problems will ask you to solve the trig equation within 0 to 2 pi. So this is a really common range of answers that we'll be working with, 0 to 2 pi. And notice how I included the equal to bar on the left, but not on the right. And that's just because on the unit circle, the angles 0 and 2 pi are the same thing. So we don't want to be redundant and include the same position twice and just call it two different things. So we don't technically include the 2 pi, it's just every solution up to 2 pi. So before we look at any actual examples of solving these, we're just going to show you how to check your solutions first. And as long as you always do that extra bit of work and check your solution, you'll always know if you're right or not. Also, it will be important to do that because we're going to ask you to answer just within the domain, or the range, from 0 to 2 pi. So let's just check that first, because we're given two potential solutions, pi over 3 and 5 pi over 3, and the equation we're looking at is 2 times cosine of x minus 1 equals 0. So let's just make sure that these two angles are within the range of 0 to 2 pi, and obviously pi over 3 is, because that's just right there. And so that would be 1 pi over 3, 2 pi over 3 would be here, and then 3 pi over 3 is just pi, 4 pi over 3 is down here, and then 5 pi over 3 is there. So yeah, both of these are within the range from 0 to 2 pi, just like one revolution around the unit circle. So then I'm going to just plug this value into the equation for x and just see that is true. So I'll evaluate this first. I'm asked cosine of pi over 3, and if you think about where that pi over 3 angle was, right here, that is a tall and skinny triangle, so the cosine value, or the x value, is 1/2, and the y value is square root of 3 over 2. All I care about though is the cosine value, which is the x value, so 1/2. So this is 2 times, well, I just evaluated this and got 1/2 minus 1 equals 0. 2 times 1/2 is just 1. Minus 1 equals 0, and 1 minus 1 is 0, so that works out. So for this one, we'll just plug 5 pi over 3 in for x, and evaluate this first. So we have 2 times, and then I've got to figure out cosine of 5 pi over 3. Remember that angle 5 pi over 3 is down here, because 6 pi over 3 would be the same as like 2 pi, that would be all the way around the circle. So this is 1 less. But the fact of the matter is, this angle has the same cosine value as it did up here. So it's still 1/2, and then minus 1 equals 0. So again, this is the same situation we had over here, so of course this is going to work out, and it's a solution. So let's try our first real example here. Again, we're solving within the interval from 0 to 2 pi, and the equation is very similar to what we just looked at, except for it's equal to 1 instead of 0. But I'll add 1 to both sides, and then we've got 2 cosine of x equals 2, and divide both sides by 2, so cosine of x equals 1. So now I just have to think about, on the unit circle, where does the cosine value equal 1? And cosine is an x value, so if I want an x value of positive 1, that would be this angle, which is just 0. We could call it 2 pi, but remember we're not actually including that. That's why we have parentheses here around the 2 pi. So when I'm solving this last step, really all I'm doing is just drawing on the unit circle where that angle would be. And we're saying that angle is 0. And for now, you might want to put a degree sign or the word radians just as units, just so that we know that the solution we're getting is an angle. It says we can check our solutions algebraically or graphically. We just did algebraically in the last example, so I'm going to check it graphically this time, just to show you that you can do it this way. So I'm going to graph this, 2 cosine of x minus 1. So the minus 1 means that we have a midline at -1, so I'll draw that in. And then the 2 in front means that we have an amplitude of 2. And remember, cosine starts at its maximum point, so it's going to start 2 units above this midline, which would be right here at positive 1. And if the period is 2 pi, like it normally is, it'll repeat out here. And then right in the middle of those two, it'll have a minimum point. So this is just a really rough sketch. And I'm only worrying about graphing it to the right because we're only looking for a range of 0 to 2 pi. We'll see that they only meet at one spot between 0 and 2 pi. It's right there. I guess technically over here too, but remember that's at 2 pi and we're not including that value. So the answer works. All right, so let's try number 2. And actually this looks very similar to one of the first examples we tried to solve in this video. So I'm going to add sine of x to both sides. And that would give me 2 sine of x. But actually in the same step, I'm going to subtract the square root of 2 from both sides, just to save some time and space here. So we'll have negative square root of 2. Then just divide both sides by 2. So you can see I'm just trying to isolate the trig term. And here we get negative square root of 2 over 2. So now I've got to think about on the unit circle, this is the point where we just have to draw this out. So if I'm looking for where we have a negative sine value, remember sine is like a y value, so I'm going to draw 2 angles with negative y values. So that'd be down there in the third and the fourth quadrant. And it says that the sine value is negative square root of 2 over 2. So sine is like that y value again, so I'm going to label the y value, or like the height of these triangles, as negative square root of 2 over 2, and it's the same for both of these. So remember, this value comes from a 45, 45, 90. You may be used to 1 over the square root of 2, but it's going to be really helpful for you to just know both of these values are the same. So if these are 45, 45, 90 triangles, or in other words like pi over 4 type reference angles, well this would be 1, 2, 3, 4. Pi over 4 would make pi, so this is 5 pi over 4. And then to get all the way around, this is 5, 6, 7 pi over 4. So to solve this equation, I'm saying that x equals, I'm just kind of plucking that x out of there, and saying that it equals 5 pi over 4 and 7 pi over 4. And you can just write your solutions as a list like that. So to check your solutions, if you want something you can do that's a little bit more interesting than just like plugging these back into the equation every time, especially because it said you can check it graphically, if you want, just graph the left side and graph the right side of these and see where they intersect. Now, if you want to do that on your calculator, that's fine, but it might be kind of a pain in the butt. If you type it into Desmos, it actually goes pretty quick. So I'll just type sine of x plus the square root of 2 into one line, type negative sine of x into the other line, and then I'll go over here and change the domain so that the x value, like the window that I'm seeing, is only going from 0 to 2 pi, because that's all I care about. And then here's your two graphs. If you just look at where they intersect, you can see it's 5 pi over 4 and 7 pi over 4. And it tells you even as like a pi over 4 type of an answer, it doesn't give you a decimal. So it works really nicely. All right, let's try example number 3. So we'll add 2 to both sides. So we'd have the square root of 3 times the cosecant of x equals 2, and then divide both sides by the square root of 3. So the cosecant of x equals 2 over the square root of 3. Now I'm not super familiar with finding cosecant values on triangles, so I'm actually going to change this into sine. So cosecant of x is going to change into sine of x, and the way I did that is I basically reciprocated it. I flipped it upside down. So I'm going to do the same thing on the right side. You can just flip that fraction upside down and get square root of 3 over 2. And this is something I'm much more used to seeing. So if we think about on the unit circle, remember this is the step where we just have to draw it out. I'm looking for positive sine values, positive y values. That means that we're going to be up in the first and the second quadrant. And if the y value, or the sine value, is square root of 3 over 2, that would be like the sides of the triangles out here. So we have tall and skinny triangles, because this value on the side is square root of 3 over 2, and the bottom side would be 1/2. So if this is the big side, that means this is the big angle. That means it's a pi over 3 type of an angle. And then this one would be 2 pi over 3, because then all the way down here would be 3 pi over 3 or pi. So we have pi over 3 and 2 pi over 3. So those are the solutions to this equation. So again, to check that, you can just type in square root of 3 times the cosecant of x minus 2 into one line, and then just type y equals 0 into the other line, and see where they intersect. And you'll see it crosses at pi over 3 and 2 pi over 3. Example 4 is very similar to the last one. We're just going to add 4 to both sides and then divide by 3 real quick. Now this part's a little bit different because we don't just have secant of x equals some value, we have secant squared. So we have to get rid of that squared by taking the square root of both sides. Now on the right side, I can take the square root of 4 on top, that's just 2, but I can't take the square root of 3 on bottom, so I'll just leave that as the square root of 3. But remember, every time you take a square root, you got to include a plus or minus in front. And just like the last problem, I'm not very familiar with secant, so I'm going to flip that around into its reciprocal, which is cosine of x, and I'm going to flip the right side as well. So we get plus or minus the square root of 3 over 2. And it's not like we have to flip over the plus or minus into a minus or plus or anything like that. That's not a thing, so just worry about flipping the value here. So now I just have to draw this situation. So on the unit circle, I'm looking for angles that have a cosine value of square root of 3 over 2. But it can be plus or minus. So positive cosine values are to the right where we have positive x values. So I'll draw one triangle here and one triangle here. And I know that they're going to be like short and wide because the cosine, or the x value, is the big value. So that's going to be the square root of 3 over 2 on the x-axis. So I just wrote that kind of big right in the middle. And then the hypotenuse is 1 for both of the triangles. But we can also have negative cosine values over here. These x values would be negative square root of 3 over 2. So we actually have 4 different angles we have to name here. So the first one, this is a small angle because it's across from the small side. So that would be a pi over 6 angle. And then all the way over here, that's not quite to pi or 6 pi over 6, so it's just 5 pi over 6. The next one's actually one more than pi, so that one's 7 pi over 6. And the last one is really close to 2 pi. In other words, it's really close to 12 pi over 6, but it's one less. So this is 11 pi over 6. And again, to just check these solutions quickly, I'm going to plug into Desmos 3 secant squared of x minus 4, and then in the next line, y equals 0. And you see that, yep, it crosses at pi over 6, 5 pi over 6, 7 pi over 6, and 11 pi over 6. Now, number 5 is already factored for us. It says sine of x times this other factor, sine of x plus 1, equals 0. Don't bother factoring something unless it's set equal to 0. But since it is set equal to 0, we can just take these factors and split them up and set them both equal to 0 separately. So over here we have sine of x equals 0, but we do have a little bit more work we have to do. Like, let's draw that out. Where does the sine value or the y value equal 0? Well, that would be off to the right or off to the left. This is the point 1 comma 0, right? So the sine value or the y value is 0. Same thing over here, this is negative 1 comma 0. But the angles there, the actual angle, that's the angle 0, and this is the angle pi. So far we have 2 solutions. We've got x equals 0 and x equals pi. And let's see what happens over here. So I'm going to subtract 1 from both sides, and then I'd get sine of x equals negative 1. And then to solve this, again, just like draw it out. So where does the sine or the y value equal negative 1? Well, that would be straight down, and that angle is 3 pi over 2. So I have one more solution I have to add to my list. And again, just to check your work quickly, type sine of x times sine of x plus 1 into one line, and then y equals 0 into the next, and you'll see, yep, it crosses at 0, pi, and 3 pi over 2 again. All right, on to number 6, and this example is a little bit trickier because now we don't have just one trig function showing up, we have secant squared plus tangent squared, and this is just a typo, there's supposed to be an x there. So when we solve these, if possible, we want to try to get down to just having like one trig function. What's lucky is that secant squared and tangent squared are related with the Pythagorean identities. So I'm going to try to get rid of secant squared and turn it into a tangent squared. Because there is one identity that says tangent squared plus 1 equals secant squared. So I'm just going to replace that. So secant squared is becoming tangent squared plus 1, and then I just have to write the rest of the equation. So we still have plus tangent squared of x minus 3 equals 0. So now we have 2 tangent squared terms. So 2 times the tangent squared of x, and then I also have a plus 1 and a minus 3. So now add 2 to both sides, and then divide by 2. And again, we get down to a squared trig term. So I have to take the square root of both sides, which really just puts a plus or minus in front of that 1. So remember, I like to think of tangent as slope. So this is like saying, draw me some angles that have slopes of positive 1 or negative 1. And if the slope is 1 or negative 1, that means that the side values are the same. So like the x and the y value on this triangle will be the same. And if the triangles have the same side lengths, that's like a 45, 45, 90, or a pi over 4 type of an angle. So this one's pi over 4. Over here would be pi, that's 4 pi over 4, so this is 1 less. So this would be 3 pi over 4. This is 1 more than pi, so that makes 5 pi over 4. And this is right before 2 pi, and that would be like 8 pi over 4. So 1 less makes this 7 pi over 4. So this equation has 4 different solutions. Notice that the direction is said to go between 0 and 2 pi, and that's just kind of like pointless right now because we're only looking at one rotation around the unit circle anyways. That's going to come into play a little bit later. So to finish this problem off, I'll just list out my solutions. All right, with example number 7, we have a similar problem. We have secant and cosecant in the same problem. And I'd like to potentially get those into the same trig function if possible, but that might not be possible here. Now, I know when most people see this equation, they might want to divide both sides by cosecant of x because they see that that's a common term on both sides and you could just divide it out. But you absolutely cannot do that because what's happening here is this cosecant of x that has an x in it, that variable, that's responsible for some of the solutions in this equation. And if you just divide it out of both sides, you're just completely getting rid of part of the equation, which means you're going to miss out on some potential solutions. So instead of doing that, the trick is just subtract this over to the other side. So we're going to get everything on the same side. And this doesn't seem like it's doing much for us, but at least we got everything on the same side and it's set equal to 0. And when you see something set equal to 0, that's a clue that it might be nice to factor it. And we can do that. We have 2 separate terms here. The first one is secant of x times cosecant of x. The second one is just 2 times cosecant of x. So they both have the same term common. So let's factor that out of both of them. So I'll pull cosecant of x out, and then I'm left with secant of x minus 2 equals 0. So here it's factored, and I can just split our factors up. So in the first equation, I have cosecant of x equals 0. Again, I'm not too familiar with cosecant, so I'll flip that over, change it into sine of x, it's reciprocal, but I have to do the same thing to the right. That's actually a little bit of a problem because I have 0, which is like over 1, and if I take the reciprocal of that, that would be 1 over 0. Right? Because you can put anything over 1, that doesn't change the value of it, but now when I flip that over, 1 divided by 0 it's undefined. So this is like saying find some angle where the sine value is undefined. And that's never going to happen. If you think about the sine graph, it goes on in both directions forever. There's no point where it's undefined, like it always has values. So this equation is just kind of a dead end. It didn't give us any solutions, and that's okay. Let's take a look at the second one. I have secant of x, and I'm not going to change that into its reciprocal yet because I still have this 2. So let's isolate the trig term. I'm just going to add 2 over to the other side. And then we have secant of x equals 2. Again, now I'm not familiar with secant, so now I'll change this into cosine. So that would say cosine of x equals, and then to reciprocate the other side, that would be 1/2. So let's think of where on the unit circle we have angles that have a cosine or an x value of 1/2. Well, that's the small side, so if we have a small x value, that means it's going to be a tall, skinny triangle. And we have positive cosine values here, but also this angle right underneath it, because again, cosine is x, and so we have positive x values to the right. So if this is the long side, that means that this is the big angle, so that would be pi over 3. And then going all the way around the unit circle, well, this is close to 6 pi over 3, because that would be 2 pi, but it's 1 less than that. So this is actually 5 pi over 3. So this equation only has 2 solutions, pi over 3 and 5 pi over 3. So it is important to notice here in example 6, we had to get the same trig function. In number 7, we didn't. We just subtracted and factored. So 2 different approaches to these problems. All right, I'd say this is a pretty good place to stop in the notes if you want to take a break here and come back to it another time. If you want to just get all this done in one sitting, I'm just going to keep going through these examples. All right, so in example 8, we have sine squared of x equals 3 times the cosine squared of x. And again, I don't want to divide any trig functions out. Like, I know I could divide by cosine squared, and I guess that would give me a tangent squared over here, and then cosine squared divided by itself would just be 1. So that might be helpful, but we don't want to do that because that would be dividing out part of the equation, part of these x's, and that's going to get rid of potential solutions. So just like last time, we'll just subtract this over to the other side, get everything on the same side, because when it's set equal to 0, a lot of times that helps us out. But again, the problem now is that I have 2 different trig functions, sine squared and cosine squared. So I'm going to go back to the Pythagorean identities because I know that sine squared is 1 minus cosine squared. And it doesn't matter if you want to change sine squared into 1 minus cosine squared, or if you want to change cosine squared into 1 minus sine squared, but you just have to be careful with that one because there's a 3 in front. So you'd have to keep that 3 in front of the 1 minus sine squared. So just to avoid having to distribute that in, I just decided to change the first trig function into 1 minus cosine squared. Now this is really nice because we have minus cosine squared minus 3 cosine squared. So it's really 1 minus 4 of these cosine squareds equals 0. So I'll just add this over to the other side now. We get 1 equals 4 cosine squared of x, and then divide both sides by 4. And now we have 1/4 equals cosine squared of x. Now we just have to take the square root of both sides. So over here we just have cosine of x. But now we have square root of 1/4, which is 1/2, right? Square root of 1 is just 1, and square root of 4 is 2. But don't forget the plus or minus in front. So let's draw this out now. I'm looking for cosine values or x values that are positive or negative 1/2. So small positive or small negative x values. That means that these are going to be the tall triangles. So if this is the big side, that's the big angle. So again, we have pi over 3. We have 2 pi over 3, with that would have the negative cosine value. This would be 3 pi over 3, so then one more would make this 4 pi over 3. That has another negative cosine value. And then this last one is 5 pi over 3, and that has the positive cosine value again. So there's our 4 solutions. In number 9, it's already factored for us, and it's set equal to 0, so I'm just going to split them up and set them both equal to 0. In the first example, I'll add 1 over and divide by 3, and just to save some time here, I'm just going to start skipping some of the steps, or skipping writing them down, and just say them. Over here I'd have tangent squared of x equals positive 3, just adding that over to the right. Now again, I have to take the square root of this, square root of that. Actually got to take the square root of everything here. So we get tangent of x equals plus or minus, because we're taking the square root, 1 over the square root of 3. Don't worry about rationalizing the denominator or anything. And then over here we just have tangent of x equals plus or minus just square root of 3. So remember, let's think of tangent as slope, And then we can look on the unit circle for where we have a slope of 1 over the square root of 3. And I recognize the square root of 3 value from the 30, 60, 90 triangle. But this is going to be a small value, and this is going to be a large value. So this is like a not very steep slope. So the kind of triangle that we have that makes a not very steep slope would be a pi over 6 type of an angle. But remember, we're looking for positive or negative slopes like that. So this is a positive slope of 1 over the square root of 3. This would be the negative slope. I know like the arrow for the angle would point up to the left, but if you're reading slope, you always go from left to right, so this would be a negative slope. And then we have to take care of these angles in the bottom too. This would have a positive slope, just like the one in the top right, and then the one in the bottom right would have a negative slope, just like in quadrant 2. So we had pi over 6. This one is 1 less than 6 pi over 6, so 5 pi over 6. The one on the bottom is 1 more than pi, so 7 pi over 6. And this last one is 1 less than 2 pi. 2 pi would be like 12 pi over 6, so this is 11 pi over 6. So we have these 4 solutions, but that's not it. All of those angles that we just drew were just for this first equation. So now we have to draw out the angles for this equation. So we have positive and negative, like steep slopes. Square root of 3 is a steeper slope than the other one, 1 over the square root of 3. So the steeper slope would be like this triangle, and if this is the bigger side length, this would be the bigger angle. So that's like a pi over 3 type of an angle. And then we have a negative slope over here, that would be 2 pi over 3. Here we're back to the positive slope, and here we're back to the negative slope. And maybe a better way of thinking of this is just the fact that tangent is positive in these 2 quadrants, in quadrant 1 and quadrant 3, and it's negative in these 2 quadrants, 2 and 4. But anyways, this one on the bottom is 4 pi over 3, and then the last one is 5 pi over 3. So it's kind of crazy, but this equation actually has 8 solutions to it. The reason why it had so many is because, first of all, it was factored. So it's like we had 2 equations that we had to solve, and also both of these equations had squared things in it, so that created a plus or minus for it, and that's why we had so many solutions. In number 10, I have cosine of x on both sides. The one on the left is cubed, but I'm going to get them both on the same side. So cosine cubed of x minus cosine of x. So I'm just subtracting this over to the left, equals 0, because then I have common factors that I can pull out. So I'll take cosine of x out front, and that would leave me with cosine squared of x minus 1 equals 0. So again, we'll split these up and set them equal to 0. So where's the cosine of the x value 0? Well, the x value is 0 up here and down here. So that would be an angle of pi over 2 and 3 pi over 2. In the other equation, I guess I have to add 1 to both sides first. So then we have cosine squared of x equals 1, and then take the square root of both sides. So cosine of x equals plus or minus 1. And where is cosine positive or negative 1? Well, the x value is 1 over here and negative 1 over here. So we have angles of 0 and pi as well. So I'd say x equals 0, pi over 2, pi, and 3 pi over 2. I don't really care what order you list these in, so if you just like put these 2 together first and then 0 and pi together, that's fine. It doesn't matter what order you list them in. So 11 is very similar, and actually we have secant squared minus secant on the left, and it's tempting to want to factor this secant out right away, but remember that's not going to help us because this is set equal to 2. So I'm actually going to subtract 2 from both sides first. But now we can't factor this the same way we wanted to before. It's not helpful for me to take a secant out of both of those terms because then I just have this random negative 2 sitting there. So I'm actually going to factor this like a regular, just like trinomial. Like if this said x squared minus x minus 2 equals 0, I'd want to factor that into x minus 2 and x plus 1, right? Because negative 2 times 1 is negative 2, and negative 2 plus 1 is negative 1. But I just replaced secant of x with an x. So now I have to go back and do that again. So secant of x minus 2 times secant of x plus 1 equals 0. So now I'm just going to split these up and set them equal to 0. And actually I just moved the constant over to the other side right away. So here we have secant is negative 2, and again I'm going to flip this over into cosine, it's reciprocal, which means I have to reciprocate the other side as well, which would be 1/2. And we'll do the same thing with the other one. So secant will change into cosine again. And negative 1, if you want to put that over 1, you could flip it around and then it would be 1 over negative 1, which is still just negative 1. So let's take a look at the first equation. We've got cosine of x equals 1/2. Where the x value is 1/2, that would be the skinny and tall triangle. So we just want positive x values this time though, so I'm just going to go in the first and the fourth quadrants, try and draw these triangles kind of like each other. So if this is the tall skinny triangle, the big side here means it's across from the big angle, so this is pi over 3, and the bottom one is 5 pi over 3. So we have 2 angles so far. The next one says cosine of x is negative 1, so the x value is negative 1 way over here, and that angle is pi. So I'll say x equals pi over 3, comma, pi, comma, and then the last one was 5 pi over 3. All right, number 12, we have cosine of x plus 1 equals sine of x. Now here's a couple issues that we might run into. If I just try to subtract sine over to the other side, then I'd have cosine minus sine, and that's not a Pythagorean identity. Like, we can't use that because those are all squared, and there's nothing squared in this problem yet. So I can't change sine into cosine. I can't factor this. There's not a whole lot I can do. So this is kind of a weird step, but what I'm actually going to do is make the problem more complicated than it already is. It seems weird to do this, but I'm going to square both sides. But we're going to do that so that we can use those Pythagorean identities. Like, we need some sine squareds in this problem. So on the left, careful, because if you're going to multiply this by itself, like if you're going to square it, you do not just distribute the squared in like this. Okay, so you actually have to FOIL this out. So it'd be like cosine of x plus 1 times cosine of x plus 1. So that would be cosine squared of x, and then the middle terms and the outside terms would give me plus 2 cosine of x, and then the last terms, just 1 times 1 is plus 1. On the right side, it's easy to square this, it's just sine squared of x. So it seems like we made the problem worse than it already was, but now we can change sine squared of x into like 1 minus cosine squared of x. And I'm just going to choose to do it that way because we already have a cosine squared and a cosine term. So it seems like this one's the oddball out. We're going to change that into 1 minus cosine squared. So it really equals that instead. I just substituted it. And now I'm going to get everything on the same side because we have a bunch of cosine terms. So I'm going to subtract 1 and I'm going to add cosine squared to both sides. So we have cosine squared plus another cosine squared. So we've got 2 cosine squared of x. And then just the same plus 2 cosine of x, and then plus 1 minus 1, that actually goes away, so that's nice, and then this just equals 0. So it's set equal to 0, that's my clue that I should probably factor this, and we have 2 terms on the left. They both have a 2, and they both have a cosine in common, so I'll pull that out front, and then that leaves me with just 1 cosine of x plus 1 equals 0, so we'll split these up and set them equal to 0 separately. So 2 cosine of x equals 0, and cosine of x plus 1 equals 0. Over here, if we just divide both sides by 2, we still have cosine of x equals 0. And over here, I just have to subtract 1, so cosine of x equals negative 1. So we'll draw these out, and if I want an x value or a cosine value of 0, that means I'm going straight up and down. So that's the angle pi over 2 and 3 pi over 2. And then this other one, cosine is negative 1, on the left side. We want an x value of negative 1, so that'd be the angle pi. So x equals pi over 2, pi, and 3 pi over 2. All right, now 13 looks really weird. We've got 2 fractions on the left side being added together. And if you're going to add 2 fractions together, you need common denominators. So let's just start there, because at least then we'd have just 1 term instead of 2 complicated looking fractions. So the first fraction would need a 1 plus sine of x on top and bottom, because that's the factor from the second denominator. But the second fraction needs a 1 minus sine of x on top and bottom. And notice that I'm just doing this to each fraction individually, so I'm not affecting the right side at all. So I wrote out what we have in the numerators, but in the denominators we have 1 plus sine of x times 1 minus sine of x. And those are conjugates because we have a plus and we have a minus. They're opposite signs but the same factor other than that. And when you multiply conjugates together, you get a difference of squares. So I just know this from doing it so many times that I'm going to get 1 minus sine squared of x. And that's actually really nice. Hopefully you recognize now that that's one of the Pythagorean identities. So I could actually probably change 1 minus sine squared into a cosine squared, but let's just hold off on that for just a second. I don't want to change them into cosines yet necessarily because on top we still have sine of x, so I don't want to have 2 different trig functions if possible. But what you notice is when you add these 2 fractions together, you have a 1 plus a 1, so that would make 2, and then you have positive sine minus sine, so those actually cancel out, so the entire numerator is just 2 over 1 minus sine squared of x. So it turns out that it is actually safe to change that into a cosine. So 2 over cosine squared of x equals 8. And I don't know if you've been paying any attention, but we've run into this situation a lot where we have one number equals a fraction. And when you're solving these things, it's easy to just flip-flop these 2 things, and you end up with 2 over 8 equals cosine squared of x. So I'm going to take the square root of both sides, and actually I'm kind of running out of room, so I'll do this up here. Now 2 over 8 is the same as 1/4. So if you take the square root of 1 on top, that's just 1, and the square root of 4 on bottom is 2. But since we're taking the square root, you got to remember your plus or minus in front. And then on the right side, that just equals cosine of x. So where does the x value equal positive or negative 1/2? Well, that would be, we've been getting these angles a lot. I mean, there's only so many angles on the unit circle to work with, right? But we have positive x values over here, negative x values over here, and I made sure that the triangles are all tall and skinny triangles. So again, we have pi over 3, we have 2 pi over 3, not 3 pi over 3, skip over that and write 4 pi over 3, and then the last one is 5 pi over 3. So I'll list those out up here. And at this point in the video, I'm actually going to stop and let's cover the rest of the problems in a different video. These are noticeably different, so I want to cover them like very separate from what we've just been working on. The big thing that's different about these problems, just kind of a preview here, is the fact that we have x over 2, or we have things like 2x, and that's going to completely change like the process of solving these.